let's say we have a piece of metal here. And this piece of metal has this shape, and on one side we've got a coil. And on the other side we have a coil. We've got 5 turns on one side. We've got 10 turns on the other side. Well, the first thing we can do is we can run a current through this coil over here. So if we run a current through this coil, we're going to get current going through this wire. As the current goes through this wire, it's going to induce a magnetic field in this wire. And so your magnetic field then will move up through this piece of iron. And so what we have is really a piece of iron here, or a piece of metal. And this is going to be our north pole up here. And so our north pole then, our lines come out of it. And they actually twist around inside of the metal. The metal holds them inside. Some of them go outside, but most of them go inside. And they go down through this other coil, which is what we're going to talk about in a minute, and then back here to the south pole. And so they create this electromagnet. And this piece of metal here is not just a single solid piece of metal. It's a whole stack of laminated pieces of metal. And this stack of laminated pieces of metal we'll talk about in just a moment. But these are pieces of metal here, and it's inducing this magnetic current going around. So we have our north pole.
Thin metal, basically?
Say that again?
It's just like thin metal?
It is, yes, just laminated sheets of metal. And so as it induces this magnetic field in here, this magnetic field then is going to influence this other wire over here. And this magnetic field then, because there are, if we close this circuit over here, just like we turned the light bulb, if we close the light bulb in there, it's going to cause a magnetic field that resists that magnetic field, which then will cause electrons to flow, or current to flow in the wire. So in this case, if we attach a DC current to it, we immediately get current running through the wire. And as we immediately get current running through the wire, a magnetic field starts in the iron, the piece of metal here, our transformer, this actual transformer. And as the magnetic field starts in here, we get flux change through this wire. And so over here on this side, because the magnetic field has changed, we start to get a pulse of EMF. And that pulse of EMF then, we start to get some voltage and some current going into this wire. But as that battery stays connected, it doesn't change anymore. It's now constant. There's a magnetic field there, but there's no change in it. So it actually drops off and doesn't do anything then. And so if we detach it, we put a little switch here, and we keep attaching it and detaching it and attaching it and detaching it, we could keep getting these pulses here. But if we left it open, we would have a flat line of EMF on the other side. And if we left it closed, we would also have a flat line of EMF on the other side, because there would be no change in flux, because that's our delta phi. Does that make sense? And so then, instead of using a DC current, the real solution is to use AC current. An AC current, you can make a little symbol like that, a full wave, actually, and attach it here. This represents AC current, or AC, alternating current. And the cool thing about alternating current is that it switches directions 50 to 60 times every second. So when it goes one direction, then goes the other, goes one direction, goes the other. And so there's this constant change of direction, which means the magnetic field flips. And as the magnetic field flips, we have change in flux. That change in flux causes induction. And so instead of having this, we end up with this. And we get AC current out the other side. So let's say I have 5 turns on this side, and I have 10 turns on the other side. If I have an input voltage, my voltage on this side, just representing the voltage as V. In this case, we're going to get 2V if I have 5 turns and 10 turns. So really what we're doing is we're taking our voltage and we're stepping it up. This is what's called a step up.
Can you lower it too?
Absolutely. This is the step up transformer, and if you had it reversed, let's say you had 10 turns to 5 turns, that would be your step down transformer. And so you can have both ways. You can have the voltage step up or step down. Now, the cool part about this is that this is, once again, this is free energy, right? Can we get free energy?
I don't know.
Well, let's talk about power then. What is power? Our equation, power equals current times voltage. Then if our voltage ends up going up, then our current needs to be going down. So our power actually stays the same. So in this case, if we have our primary and our secondary, if we call this our primary side over here, the secondary, we can break it into our power in is equal to our power out, and that's in an ideal transformer. And if this power in is equal to power out, we've got our I times V for our primary on one side, and I times S for our secondary on the other side. If our voltage goes up on one side, then we're definitely going to need to have our I go down.
What's N? That's because I saw M.
Yes. Our N is going to be our number of turns. So N is our number of turns on either side. So N comes from that formula of N times our change in phi over change in T. Does that make sense? Cool. So you've got your voltage secondary and your EMF primary. If the same flux is going through each of them, same time, then it all has to do with our number of turns. And our EMF and our secondary voltage being proportionate to each other. And really, they're equal and opposite to each other. We know the flux and the time is the same. It all has to do with the number of turns. So we can set up that our voltage primary to the turns on the primary is equal to the voltage on the secondary compared to the turns on the secondary. Which, interestingly enough, then we can add one more piece to it and say that if it's the voltage to the turns, then we can say voltage primary to the voltage secondary is going to be equal to the number of turns on the primary, the number of turns on the secondary, and then with current,
Opposite.
it's going to be opposite. That's right. Nice.